Okay, it's recording. So welcome everyone. Today we are very lucky to have Jan presenting. Jan is a research scientist at Google DeepMind and is currently working on large language models. And he was telling me that he's very happy to give a talk about this nice memory that he had working on this. He received his PhD in reinforcement learning from INRIA and Meta AI, Paris. So thanks again, Jean, for accepting our invitation, and the stage is yours. Thank you.
Thanks, Luca, for the presentation. Yeah, and I'm super happy to be invited here to give a talk at the RL Theory Seminar. Last time I came here and gave a talk was in June 2021 during my PhD and during COVID, so it brings back special memories. So I'm really happy to talk about this work that I did with Tor Latimore and Brendan O'Donoghue from Google DeepMind on probabilistic inference in reinforcement learning done right. And we presented that work at NeurIPS 2023. So we focus on the reinforcement learning problem where an agent interacts with the environment to maximize the cumulative reward. And the wrinkle in RL, of course, is that the environment is unknown. So the agent maintains some beliefs over the unknowns, derives a policy which collects some data, and then the agent can refine its beliefs and so forth. So at its core, RL is about choosing which data to collect to maximize long-term return. And so it's a statistical inference problem wrapped into a control problem. And both need to be tackled simultaneously for good performance. So this notion of exploration or data efficiency, it's a major bottleneck in most practical RL applications. So many of which have been and still are studied at Google DeepMind, like theorem proving, robotics, code generation, more recently RL for LLMs. And one thing to note is that even though they've achieved remarkable results in some domains, it comes at a cost of a major cost in terms of data requirements and hardware requirements. And one of the reasons for this is that most of these practically state-of-the-art agents, they do simple local jitter exploration. So, for example, epsilon greedy or unstructured noise injection, etc. And so there's the hope that if we are able to inject some efficient exploration mechanisms, then we may get exponential speedups over these current agents and unlock new capabilities. So now that this high-level motivation is explained, and I hope that most people here will agree with that on the promise of exploration really unlocking new RL capabilities. Now I'm going to delve into the meat of this talk and basically give this high-level Venn diagram to explain that we're going to go on a journey at the intersection of these three important topics. So there's control, there's statistical inference, and there's probabilistic graphical models. So it's well known that reinforcement learning lies at the intersection between control and statistical inference. And in particular, this is often coined as the exploration literature, and it's historically mostly pertained to RL theory works. There's a host of research on this. And one of the core drivers, one of the core principles is this notion of optimism in the face of uncertainty. On the other hand, at the intersection between control and probabilistic graphical models, there's been this recent line of research that has gained quite a lot of popularity, especially in the deep reinforcement learning community, which is often coined as RL as inference. And it's led to a family of deep RL algorithms that perform really well in practice, and they're basically based on this idea of entropy regularization. And in this talk, what we're going to try to do is to bridge the gap between this view of control as statistical inference and control as probabilistic graphical models. So there's been lots of research on trying to bridge the gap between RL theory and deep RL with the ultimate North Star of trying to develop more sophisticated exploration mechanisms that can really scale and be applied to practical settings. Here, the kind of unique twist that we'll be employing is that we're going to try to use a principled Bayesian approach in order to address this problem. And the interesting thing that we'll see is that through this principled Bayesian analysis, we'll have both optimism and entropy regularization that will naturally fall out of our approach. Okay, so first, in terms of notation, so that we're all on the same page, we define the control problem as follows. So we consider really a vanilla canonical RL setting where the agent interacts with the environment modeled as an MDP, which has a finite number of states, actions. It's a finite horizon problem where the horizon length is denoted by L. And we have time inhomogeneous transition dynamics P, mean rewards R, and initial state distribution rho. And so, we define as standard the policies pi, value functions v, and the aim is to find the optimal policy. And in the RL problem, we have both transitions and rewards that are unknown. And as such, the optimal policy and optimal value function are unknown as well. And note that since we're in the Bayesian RL setting, these quantities, pi star and v star, are random variables. Right. So first, I'm going to explain a bit this popular RL setup of RL as inference, why it's been so popular in the literature, but also what is its key shortcoming. So RL as inference, if there's one tutorial and review to really look at that kind of encapsulates everything, is this popular one by Sergey Levin, and note that it's been cited a lot, on RL and control as probabilistic inference. And here the high-level idea is that we're going to model the MDP as a graphical model. So we have these states and these actions that represent a trajectory. And what these works do is, of course, at each time step, there's an observed reward, here denoted by R. And they are going to augment this graphical model with these optimality variables, gamma star L. So these variables basically mean that time step L is optimal, quote unquote, in some sense. And what all these works do is they make a quite surprising and peculiar assumption, which is that the probability that a time step is optimal, so that gamma star L is equal to 1, is going to scale exponentially with the local reward. So this at first glance seems quite of a surprising assumption. And in fact, the reason why it's so popular is that it's actually quite mathematically convenient. So it's easy to do inference on these gamma star variables, which are now observed, depending on the exponential of the reward. And in fact, it's been shown that in special cases like deterministic MDPs, we can exactly recover the framework of maximum entropy RL. And this is well known to be a good heuristic for exploration because it naturally uncovers entropy regularization for the policy, which means that the agent is going to converge less quickly to a deterministic policy. And so it's going to explore locally a bit more. And using this surrogate potential for inference has actually generated a family of very popular deep RL algorithms like soft Q-learning, soft actor-critic, MPO, etc. And it's seen like quite good success in domains where efficient exploration is not really a bottleneck. However, the downside is that this notion of RL as inference completely ignores any notion of epistemic uncertainty. So it constructs invalid posterior estimates of optimality. And so it's been shown that it can drastically fail in some very toy RL problems, like even like toy bandit problems, where the associated strategies are going to have linear regret. And so not only cannot it perform efficient exploration with this choice, but also the way this RL as inference framework has been described in the literature is, I would say, quite misleading and anti-pedagogical in the sense that it misuses some words like posterior, like optimal, which means that many people are confused and believe that this is the proper way of doing inference on unknowns on the MDP. But this is not at all the case. And so to this end, here we're going to try to put on our principled Bayesian hat and see whether we can derive a principled approach for RL as inference. So the first step is to recall what the key object of interest is in RL's inference, and it's this gamma star optimality variable. And in fact, it has never been formally defined in the literature. So this, as a first step, is what we're going to do now. We're going to define this quantity. So it's defined for each state action pair SA and each time step L. And it's basically the event that state action pair SA is reached at time step L in a given rollout of the optimal policy. Now note that this is a random event. It's random because the environment may be stochastic. And so if we have two different rollouts of the optimal policy, they may lead us to two different places of the state space. And we can mathematically write what, yes, Chava?
Yeah, I'm just not clear to me it's well defined when you have multiple optimal policies. Is it true that it's well defined, or like it's going to be specific to which optimal policy you choose?
So here, yes, that's a good point. Here, we basically assume implicitly, even like the way we mathematically define it, that there is like a single optimal action at each state.
Okay.
In the case of multiple, we can break ties arbitrarily, and in that case, we will get the same derivations. So here,
sure, but like then it would depend on like how actually broke the ties and like
exactly.
Yeah. And that have some consequences for the rest, or like we will see, I guess.
No, it doesn't have a consequence for the rest. But that's a good point, that there's a little overload in notation, which assumes that we are breaking ties arbitrarily. Yeah, exactly. And in that case, we can basically write this formal definition. And the key idea is that basically it's a recursive definition that is only stipulating that if we're optimal at time step L+1, then this implies that we've been optimal up to this point at the first L time steps, and we've taken optimal actions, right? And once we have this like formal recursive definition of this random event, then what we're going to do is consider a Bayesian RL approach, which is that the agent has some posterior beliefs about the MDP that is represented by this distribution phi. And now the key object that we're really going to focus on during this talk is the posterior probability of trajectory optimality, which is this posterior probability of here this trajectory optimality event. And the first key result that's going to have interesting consequences is that in the case of known P, and I'll defer later to the case of unknown P, we have the interesting property that this P of gamma star, which is basically the posterior probability of trajectory optimality, is in fact an occupancy measure. That is to say, it's a stationary state action distribution, so it satisfies the set of flow equations in the MDP. So what's very interesting about this result is that it means that if we have access to P of gamma star, then we can very easily sample with the induced policy, which is the standard way of going from occupancy measure to policy, which is simply by marginalizing over the actions. And this is powerful because then it means we can readily execute something in the environment and solve a control problem, as long as we have access to P of gamma star. If we kind of rearrange these terms, yes, Chava?
Yeah, so these state occupancy measures for discounted MDPs, like you have this discounted probabilities and whatnot, like is this what we're doing or not? Or like, can you go back?
No. Yeah, so here we're working on we've got a finite horizon problem.
Okay, and you are assuming that for each stage, the state action space is separate from the state action space you would get for a different stage.
Exactly, yeah, we're considering the layered assumption.
Okay.
Yeah.
Good. Okay, layered, yeah, okay.
Yes. Exactly, yeah. I think it should be possible to maybe extend this to other setups like the discounted case, but yeah, for now we really assume the simple finite horizon and layered setup.
Okay.
And so if we massage this quantity and we use Bayes' rule, then we have an interesting equation, which is basically to say that this policy is going to sample actions according to the probability that they're optimal under pi star, conditioned on the fact that the state has been reached optimally up to this point. So this conditioning on the state having been reached optimally up to this point is quite interesting and peculiar. And I'm going to show in a very simple example right now why it's actually very important to have this conditioning on state optimality. So let's look into this toy example where we have which we call the bus stop MDP, but it's very similar to like the chain MDP or other type of MDPs constructed in the literature, where we have our robot agent here that starts at state S1, and basically there's the bus that goes from S1 to SL, and so the agent at every step can basically decide to stay on the bus, and then it incurs a little positive cost of delta, or it can decide to exit the bus and then incur a cost or a reward of 0. And so the only uncertainty that the agent has is at the end of the bus line, so this state SL, where according to its beliefs, there's equiprobably either an ice cream shop or there's not. So if there's an ice cream shop, then the agent has a reward of +1. And if there's not, then it has a reward of -1. And note that the presence or not of the ice cream shop is something that's fixed across learning. So it doesn't change at the beginning of each episode, right? There's either an ice cream shop or there's not. And so naturally we can see that for the agent to solve this kind of small problem, it should go straight away to SL, because that's the only state where it has uncertainty, and then it can resolve its uncertainty there. So it's interesting to see how some popular approaches would work. One of which, for example, is epsilon greedy. And we basically see that this is going to induce poor exploration because the probability of reaching the final state to resolve its uncertainty decays exponentially with the length of the problem. And the reason is that since here in expectation, the reward at the final state is going to be 0, basically we see that the optimal strategy is, for example, in S1 to directly exit so that it doesn't incur the cost here. And so this means that at every time step along the chain, it's going to allocate a lot of probability to exit the chain, which means, once again, this exponential dependence in the probability of reaching the terminal state and resolving its uncertainty. So maybe a more interesting thing would be, okay, let's say we have access to the optimal policy pi star. What about looking at the behavior of the marginal here? So the posterior probability over pi star. And here we see that, interestingly, we have a similar issue of caused by poor exploration, because at each time step, the agent is going to allocate a 50-50 chance of either exiting the chain or keeping on going. Once again, because the expected reward here under the posterior is 0, and it's also 0 to exit. Which means that once again we have this exponential dependence on the depth of the problem in order to reach the state. So here, interestingly, if we condition on this gamma star quantity, so if at each time step where we're in a given state, we condition on the fact that we've behaved optimally at this point, then we are able to recover efficient exploration. And this is exactly the P of gamma star quantity that I explained earlier. And let's, step by step understand why that's the case. So if we start in the initial state, then there's basically a 50-50 chance to either exit or to keep on going. However, if we're in S2, then conditioned on the fact that S2 has been reached optimally, this must imply that there is an ice cream shop at the end, because otherwise the agent wouldn't have gone to S2 in the first place, it would have directly exited the chain. And this means that condition on S2 being reached optimally, this means that there is a reward of +1. And so the agent's behavior is going to say, I want to go to SL. And so it's going to allocate a probability of 1 to stay on the bus until it can resolve its uncertainty. And so this is why here there is going to be an efficient exploration mechanism where the probability of reaching SL is going to be 1/2. And this is because, in other words, there's only 2 consistent trajectories in this MDP here. If there's an ice cream shop, it's to go all the way to the end. And if there's no ice cream shop, it's to go straight away and exit the bus. Going to S2 and then exiting is not optimal in any situation, in any belief. And same for the other states. And to condition on this notion of state optimality enables to ensure consistency of the trajectories. And so we see that once we're in S2, we're going to all the way go to the end, because it's never optimal to go to S2 and then exit the chain. Yes, I think we have a couple of questions.
Audrey first.
I just have a clarification question about this gamma star object. So is it binary? Because I thought it was like a distribution over states or something. Maybe I just missed something in the previous slide.
Maybe I just asked my question because my question is the same. I said that gamma star was just like some deterministic thing. So if you condition on it, nothing really changes. So if it's not random, if it's not an even, then like formally, like what does this mean? Like gamma star.
This is a random event. Exactly.
Like what is the random there?
So basically, the random event is whether for a given rollout of the optimal policy, whether basically in a given state, this has been reached by the optimal policy in a given rollout. And it's random because each rollout is going to induce a different trajectory.
Okay. This is a bit confusing because if our policy is not the optimal policy, then like, wow. So somehow the random variables that are for I don't know, the states for the optimal policy. Audrey, like, do you understand what's going on?
Oh, I was going to ask if like this probability sub phi, that randomness is over like your belief over the MDP, as well as like the transitions of each MDP. Right?
Yes.
Like okay, I see.
Yeah, exactly. Yes.
I see. Yeah, and the conditioning on gamma star is like you condition on like you have a given trajectory.
Exactly, and you condition that realization. Yeah, so this is exactly this.
Maybe you can explain that better for Chalo than I can, but okay, thanks.
Yeah, so this definitely basically incorporates the uncertainty due to the fact that the environment is stochastic, and so we may have different rollouts of this. That's why we call it like the trajectory optimality, because we should really see it as something that's at the trajectory level, and so it's a random event that depends on the trajectory. So of course, here in this talk,
so formally this gamma star, can we go back to the formal definition?
Yeah.
Okay. So it's basically, okay, I'm confused now because the actions are not indexed by time. Okay, so it's just the last action, but like the previous action. So I see state variables. Those are the random variables.
Mm-hmm. Yeah, exactly.
In the MDP, and the randomness involves the bit about like whether the ice cream shop is there or not, and everything else. But then we are executing some policy, and that governs basically the random, like the probability of the state being this or that. But then you're talking about that, okay, under like some extra condition that the optimal policy reaches this state. It's like I'm confused now because like I don't see in the equations this. I only see in the equation that maybe I should read more carefully.
So here, the two sources of randomness with respect to the environment. It's exactly this. It's at the state level. So it's this one, which is basically, is it sampled from like what's the initial state distribution row, and then there's of course the transitioning at each step, which is defined by here, where of course given the state and action pair, the environment is going to with certain probability lead us to another state S prime, and this is going to be encompassed here in this event. And I think, like, basically, of course, so this toy example doesn't incorporate any randomness in the environment, but I think, like, the high level takeaway is if you're in state S2, right here, as I was explaining, if you don't condition on the fact that you are optimal, then if you just, like, take the marginal over the optimal policy, then that is basically going to be a 50-50 chance to keep going. Here, the key insight is if you condition on the knowledge that you've been optimal, then this is going to discard some non-consistent behavior. And so, for example, it's going to say, no, actually, you should never go down here, because if you've acted optimally up to this point, it means you have to go all the way to the end. Another way of seeing it is, the Thompson sampling algorithm only works if you sample your MDP at the beginning, and you get the policy, and then you're consistent with it across the entire episode. So it's well known that Thompson sampling cannot resample at each time step. Otherwise, you won't have consistency. And this is the same idea here, is you basically just want to ensure consistency across your episode. And this is what the conditioning ensures.
I think that I'm just, like, bogged down by the notation, so I would just ignore that. I don't understand your notation because I understand what you're saying otherwise. Okay.
Yeah, hopefully we can, like, later in the talk, this will be here. So ultimately, what we've seen is that this posterior probability of trajectory optimality here, this P of gamma star object, the good thing is that sampling from it yields efficient exploration. And in fact, later we'll see, some regret bounds on this. And however, the bad thing is that computing it is totally intractable in most cases. So it involves some complicated integrals that are hard, that are completely intractable. And so now the key step is going to try to derive a tractable way of approximating this P of gamma star. And this is going to lead to tractable algorithms that efficiently explore. So now we're going to look into having a variational Bayesian approach. So what I mean by variational is we're going to try to construct an optimization problem whose solution is going to give a good approximation of this P of gamma star. So typically in variational Bayesian inference, we want to solve an optimization problem, which is to minimize some notion of distance, like a KL divergence, to the unknown probability of measure of interest. So here, this P of gamma star. Here, unlike in most variational inference approaches, we don't have access to samples of that. So it means we can't really do it this way. The key insight is actually we have to remember that we're solving an oral problem here. So in other words, we don't really care that much how tight we are with respect to this. What we really care about is whether the policy induced by our approximation of this quantity is actually doing well in an RL sense. So is it accumulating a good amount of reward? And so this insight is going to make us embed the notion of value functions into our optimization problem. And so now the technical question becomes, how do we relate gamma star, so the notion of trajectory optimality, to V star, which is the optimal value function, and which we recall, since we're in the Bayesian case, is a random variable. So first, we can take a look at the special case of multi-arm bandits, and maybe that will explain a bit more what this gamma star quantity is. Because I agree that it is a bit misleading in the MDP case, where we look at the level of trajectories, but at least in the multi-arm bandits problem, it's a very simple quantity. So hopefully it can give us some intuition there. So basically, gamma star A is simply the event that arm A is optimal. So here we know the optimal arm by A star. And so it's simply this event, because we don't have any notion of trajectories in multi-arm bandits. And in that case, we can very simply write the relationship between V star and gamma star as follows. The expected optimal value function under the posterior, it's the expected maximal reward. And then we can use the law of total expectation to sum over the arms the probability that arm A is optimal times the expected reward of that arm, conditioned on the fact that it's optimal. And if we plug in the definition of this event, then basically we have this relationship between gamma star and V star that pops up very naturally. So now the question is, okay, can we extend this to the general MDP case? And as we've been discussing, the notion of trajectory optimality here, gamma star in the general RL case, is much more subtle because there may be an exponential number of optimal trajectories that can lead us to a given state. But in fact, we can actually leverage the MDP structure and come up with a very similar and quite simple formula, which is to say that the expected optimal value function under the posterior and taken at the initial state is equal to the sum over steps L, state action pairs SA, of the posterior probability of trajectory optimality, so this is the object that we care about, times the expected mean reward under the posterior conditioned on trajectory optimality. That is to say, conditioned on the fact that state action pair SA have been reached in an optimal way. And here we can decompose this in two. Here we have, well, our object of interest, so that's great. And the second part is a bit trickier because it relies on this conditional expectation here. So now the final step is going to be, okay, let's try to control this quantity and remove the conditioning. And so to this end, we're going to turn to information theoretic tools, which are basically going to help us to decompose and remove the conditioning on gamma star. And so we have this conditional expectation that can be upper bounded by the non-conditional expected mean reward, plus an extra term where we see that the probability of trajectory optimality, this P of gamma star, is going to be ejected as a standalone term inside here of a log function. And so the extra objects that pop up, first of all, we've got this sigma squared LSA, which is a measure of the local epistemic uncertainty of the agent at the state action pair SA and step L. So this, formally speaking, it's the sub-Gaussian parameter of the mean rewards under the posterior. And we also have in blue here these tau L SA variables, which can be seen as temperatures. We'll see why later they can be seen as temperatures. And they're actually free variables. So this upper bound holds for any positive choice of tau L SA. Right. And now if we kind of put everything together, we basically get the following interesting result, which is that the expected optimal value function is going to be upper bounded. So we're going to, use this core idea of optimism by this function L, which is a function of P of gamma star, so our object of interest, and a vector of temperatures tau here. And so that's going to lead us to our variational approximation. And if there's one chain of inequalities to remember, it's this one, which is basically that the expected optimal value function is upper bounded by this L function, which is computable. And since we want this bound to be as tight as possible, we're going to minimize it over the temperatures tau. And then, so, this is our object of interest. The key insight to recall is that this is an occupancy measure. And so we can further upper bound this by taking the maximum over lambda, the occupancy measures. And so this gives us a convex-concave saddle point problem. It's got the nice properties that it's convex in tau, it's concave in lambda, and the set of occupancy measures is a convex set. So we basically have a tractable optimization problem that can be solved with modern optimization solvers. In fact, it's an exponential cone program. And so this corresponds to vapor, our variational approximation of a posterior probability of optimality in RL, this objective here. And the interesting thing is that it's possible to show theoretically that the solution of the variational approximation is close in some sense to our original quantity of interest, P of gamma star. So when I say in some sense, it's with respect to some measure of KL divergence. But also, more importantly, since we're RL practitioners and we want to have a good policy behind it, we'll see later that actually running this policy gives low Bayesian regret. So now, before I go into the regret guarantees, I think one interesting thing is what the heck is vapor doing? Because if we look at this equation, it looks quite complex at first glance, but actually there's a very simple and appealing interpretation of what is happening. So first of all, recall we have a zero-sum two-player game. We have a policy player, lambda, and we have a temperature player, tau. And we respectively want to maximize and minimize this common objective here. So now we can decompose this objective into two simple and interpretable terms. The first one, it's simply the dot product between the occupancy measure and the reward, to which we augment an optimistic bonus that depends on the epistemic uncertainty. So this is basically the principle of optimism here. And we have a second, more intriguing term, which is basically a measure of regularization of the occupancy measure lambda. And this regularization is weighted for each state action pair by the temperatures tau. So what's interesting is that we see that the vapor objective naturally uncovers two very popular exploration mechanisms, optimism and entropy regularization. And the extra kind of unique algorithmic flavor that vapor is advocating is that these two exploration mechanisms, optimism and entropy regularization, should be adaptively tuned for each state action pair through the choice of temperatures tau. So up to this point, we've only cared about the case of known P. So where we can basically sample, we can compute the simplex here over the occupancy measures. And the natural question is, okay, what about the unknown P case, so the more realistic RL scenario? And for this, we derive a generic reduction that enables us to take any Bayesian algorithm in the unknown P case and to translate it to the known P case. So this is a generic reduction that could be of independent interest, but in particular, we're going to instantiate it for vapor. So formally, we basically have our original posteriors with beliefs represented by here R and P, and we make the extra assumption that the prior over the transitions is Dirichlet. And the way our reduction works is that we're going to transform the posteriors in a way that we're going to eliminate all the uncertainty on the transition dynamics. And now the belief of the agent is that the transitions are simply the mean transitions under the posterior. And since we've completely eliminated uncertainty over the transitions, we're going to add extra uncertainty on the rewards through this psi random variable. And so now the new beliefs over the reward are going to be the mean reward plus this Gaussian distribution, which is zero meaned, and it has a carefully tuned variance to represent the uncertainty both on R and on P. And the very interesting thing about this reduction is if we apply it at the beginning of each episode, then if we have a regret bound in the known P case, so in these transformed posteriors, then this directly implies a regret bound in the original scenario where we do not know P. In other words, if we have a Bayesian algorithm with a regret bound for known P, we can apply this reduction and we get a regret bound for unknown P. And this is exactly what we're going to instantiate for vapor, which means that practically to go from known P to unknown P, we only do two little changes. The first one is we consider the expected transitions here in the simplex of occupancy measures, and we're going to optimize over that. And second, we're going to consider a larger measure of epistemic uncertainty here, the sigma hat that's larger than the original sigma. And we basically recover a regret bound here. So up to this point, we saw the vapor optimization problem. I just need to explain, but it's going to be very simple, how to rigorously transfer it into a learning algorithm. So we consider an episodic interaction of n episodes. And so the way the algorithm works is at the beginning of each episode, we're going to solve the vapor optimization problem with the data that we've accumulated so far. And then we're going to execute the induced policy. So it's as simple as this. And to measure how well our agent is doing in terms of exploration, the aim is going to minimize the base regret here over capital T time steps. So here, T is equal to N times L, where we recall L is the horizon length. And so the base regret is formally defined as the expected regret in MDPs N that are sampled under a known prior phi. And so the regret bound that we obtain is the following. We basically have that the base regret up to time t is upper bounded by this sublinear function in t, so it's in the square root of t. And in fact, we have near optimal dependency. So we have this L square root of SAT, which is tight up to square root of L with respect to the lower bound. And this bound is basically also achieved by other existing Bayesian algorithms like PSRL and K-learning, as we'll see later. To obtain this bound, we need a set of assumptions that are listed here as follows. So we need bounded mean rewards, sub-Gaussian reward noise. We need independent Dirichlet prior over transitions, and a layered state space. I'm not going to go in detail of these assumptions. The only thing to remember is that these set of assumptions are exactly the same as ones that are considered in the literature for Bayesian algorithms like PSRL and such. So there's no difference there. Of course, some of these assumptions are quite strong, and I think it's an interesting question whether it's possible to partially or totally remove some of them. But the key takeaway here is that thanks to this guaranteed regret bound, we have the property that vapor is performing efficient expiration. And in fact, if we were to use P gamma star exactly, we would have the same regret bound here. The main advantage, instead of using P of gamma star, which is not tractable, is that here with our variational optimization problem, we get a tractable solution to it. And in fact, it's amenable to online stochastic gradients, and that's what I'll explain a bit later with the DeepRL variant of vapor. One thing to highlight is that there's a stream of work, of course, working more on frequentist algorithms, which are indeed able to obtain minimax regret bounds. And I'm not going to go in the arguments of the pros and cons of frequentist algorithms or Bayesian algorithms. But one thing that's interesting to highlight is that the vapor algorithm is naturally producing stochastic policies, which is empirically desirable and closer to what's done in DeepRL. And also it produces stationary policies. So what I mean by stationary is that the policy doesn't depend on the episode index, whereas most frequentist algorithms tend to produce deterministic and non-stationary policies. Right, so now I'm going to try to explain a bit some connections with existing algorithms to show that actually P of gamma star is deeply rooted in many expiration strategies. And the first connection, of course, is to the celebrated Thompson sampling algorithm, also known as posterior sampling for RL. So this is a very popular algorithm in sequential decision-making. In the MDP scenario, what it does is it needs to maintain a model over the MDP, so over rewards and transitions. It's going to sample from it at the beginning of each episode, compute the optimal policy for the sample, and then execute it for the episode duration. And it gets, as I was saying, the same L square root of SAT base regret bound as vapor. The very interesting thing, which actually sheds a new light on this very popular algorithm, is that Thompson sampling is implicitly approximating P of gamma star. And this can be shown by basically if we take the occupancy measure of a Thompson sampling sample, and we take the expectation over all these samples, we can prove that this is exactly recovering P of gamma star. So this shows that Thompson sampling is implicitly approximating P of gamma star by a sampling mechanism. And so it sheds a new light on this algorithm, and also it shows a very deep connection with the vapor algorithm that we presented, which is rather doing an explicit approximation of the same quantity, P of gamma star, through a variational mechanism. It could be interesting to compare Thompson sampling and vapor, in particular the way they do it algorithmically, since Thompson sampling is based on a sampling procedure, so it needs to maintain a model over the MDP parameters and sample from it, which can become prohibitively expensive if the MDP is large, whereas what Vapor is doing is solving a differentiable optimization problem. So this really more naturally paves the way towards using differentiable neural net architectures, as I'll show later. In terms of exploration mechanisms, Thompson sampling relies on this notion of stochastic optimism, whereas Vapor, as I was showing in the interpretation, is basically using explicit optimism through a bonus on the reward and entropy regularization. And these are very appealing algorithmically. And finally, for those interested, we can also point out some settings such as multi-agent MDPs, often known as matrix games, or constrained MDPs, where it's been already shown in the literature that Thompson sampling suffers linear regret, whereas suitable modifications of Vapor could obtain sublinear regret in these special cases. Another interesting connection is to K-learning and ERSAC, which are algorithms that have been recently introduced by Brendan. At a high level, what K-learning does is it's basically doing soft Q-learning, and it's adding a learned scalar temperature that balances optimism and entropy regularization. And once again, it gives the same base regret bound. And the interesting thing is that, okay, we see there is a deep connection with Vapor. The main difference is that K-learning learns a single scalar temperature to balance out optimism and entropy regularization. Whereas what Vapor is advocating is we should do this on a per state action basis. Of course, this is much more powerful because it means the agent has much more fine-grained control over the exploration-exploitation trade-off in the MDP, depending on regions of a state space where it may be more uncertain or less uncertain. Whereas K-learning requires a single scalar to drive all this trade-off between exploration and exploitation. And conversely, we can show that if we constrain the temperatures of Vapor to be equal, then we basically recover the K-learning algorithm. And so what this is showing is that even though it wasn't derived using this variational inference approach, actually K-learning can be seen as a variational approximation to P of gamma star as well, with the added constraint that we consider uniform temperatures. Of course, the appeal of Vapor is that it's a tighter bound in theory, even though in terms of minimax dependence, it's the same. But also, it gives better performance in practice. And that's what I'll explain now. So in terms of experimental results, I'm going to focus on the deep sea environment in its tabular setup, which is an L by L grid where the agent starts on the top left. And it has to reach a treasure that's located on the bottom right here. And it's the only state with a positive reward. And at each time step, the agent can either go to the left or go to the right. And it's going to go run one row down. And so here we see that in order to reach the treasure, the agent has to take the correct sequence of actions L times. One wrong action, and it means it's impossible to recover, and it has to start at the next episode. So this is a very hard exploration problem indeed. And it's no surprise that local differing strategies like soft Q-learning exhibit an exponential dependence in terms of learning time with respect to the horizon of the problem. So here on the x-axis, we have the depth of the problem, L, and on the y-axis, we have basically the learning time. And note the log scale here on the y-axis. And so here we see this clear exponential dependence of soft Q-learning. K-learning as a principled exploration strategy is able to reliably solve the deep sea problem up to size 50 here. And Thompson sampling also does well. And we see that Vapor achieves the lowest learning time of all. The interesting thing is to note the difference between K-learning and Vapor, which highlights to the importance of tuning the entropy regularization and optimism on a per state action basis and not having just a single scalar to drive everything. Right, so up to this point, we saw a tabular and model-based no regret algorithm. And now in the remaining time that I have, I'm going to give an overview of how we can derive from this principled approach a scalable model-free algorithm. and instantiate it in deep RL settings. So the very interesting thing about Vapor is that it's amenable to online optimization. And so in particular, we could represent the policy using a deep neural net. And so we introduce Vaporlight, which is an approximation of Vapor that basically does a few tweaks, such as considering a weaker notion of weighted entropy regularization. So it's no longer on the occupancy measure, but it's just on the policy level. And this enables to apply a policy gradient formulation immediately and to implement it in deep RL settings. And note that this is a principled upper bound of Vapor. So we are losing a bit because we have this weaker notion of weighted entropy regularization, but it is still a principled upper bound, and we can derive regret guarantees there as well. And so ultimately, the deep RL algorithm, what it does is now it optimizes over the space of policy. So, as standard policy gradient formulation. And the only thing that it does compared to vanilla policy gradient is that it tunes the optimism term and the entropy regularization term here with these uncertainty estimates, sigma hat. And in our deep RL implementation, we use an ensemble of reward predictors to estimate this uncertainty here that drives both the optimism term and the entropy regularization that is weighted for each state action pair. And if we look at some results, so first we can take the same deep C problem, but now look at from a neural net perspective. So we feed in to the agent as input its location as a one-hot representation. And we see that the baseline agent, which is replay actor critic with V-trace corrections, performs terribly on this domain, which is well known because it doesn't have an expiration mechanism. Methods like bootstrap DQN, they do reasonably well at the beginning, but then their learning time completely degrades here as the environment gets bigger. If we just use a naive optimism bonus, we actually see that it is performing quite well. However, it is struggling for larger deep C problems. Whereas the Vaporlight approximation is really able to nail down this deep exploration problem and can, gracefully scale its learning time as a function of the deep C problem size. And if we inspect what's visually going on with the state visitations, we see on the left that like a vanilla actor critic agent is going to only do some local differing, and it won't be able to reliably explore the state space. Whereas on the right, a variational approach will be able to explore well, to identify the reward, and then it will latch onto it reliably and keep on accumulating positive reward. Now we've also benchmarked Vaporlight on the more challenging Atari domain. So here we're plotting as a function of the number of frames, the median human normalized score across the 57 Atari games. And here we have in black the baseline, which is this replay actor critic with V-trace corrections. And one thing that we see, and that's very well known in deep RL, is that just adding some heuristic entropy regularization does give a significant boost in terms of practical performance. And this is why it's so popular. However, as I've explained earlier a lot, this is only a heuristic, and it's not principled at all. It doesn't perform exploration in a meaningful way, and it drastically fails in domains like deep C, which require a sophisticated exploration. In contrast, if we look at Vaporlight, not only does it perform better than entropy regularization, but also it stems from a principled variational Bayesian approach. And in particular, in terms of performance, we see that it obtains the peak performance of replay actor critic in 2x fewer frames, and that of replay actor critic with entropy regularization in 1.5x fewer frames. And this is, for essentially the same computational cost. So now to wrap up, is gamma star all we need? Well, we've actually shown that gamma star, which is a core object of interest in the RL's inference setup, but hadn't been rigorously defined. This notion of trajectory optimality, or basically when we're in a given state action pair, have we acted optimally up to this point? This is actually a core concept where we can relate lots of algorithms to it. And if we take a Bayesian setup and look at the posterior probability of that random event, we can actually show that the celebrated Thompson sampling algorithm is implicitly approximating this via sampling. And we've also introduced another way of approximating this in a more explicit manner by using a variational approach. And this has led to vapor. And we've also shown that if we constrain the temperatures to be equal, we can basically recover some existing algorithms like k-learning or ERSAC. And we speculate that it could be possible to draw some further connections with existing algorithms, such as information theoretic exploration algorithms. And I think our hypothesis is that gamma star can be used as a way to basically unify and relate lots of exploration algorithms. And so this is a coherent and principled approach to RL as inference. We basically use variational inference to compute an approximation of P of gamma star. And then we solve it as a control problem by deploying the induced policy. And for a more practical takeaway, what our analysis naturally uncovers is that optimism and learned entropy regularization are very efficient in terms of exploration, both theoretically with regret bounds, but also empirically. Thanks a lot for listening, and I think we have some time for questions.
Great. Thanks, Jean, for the presentation. And okay, I think Audrey has a question.
No, I was trying to clap. Sorry.
Okay. Perfect. Then I see some other people raising their hands.
So I think there's a question on the chat by Nikolai.
Yeah, about the citation for constraint MDP that you mentioned at some point in your table, I think.
Yeah. So here, when I say that the vapor algorithm has a sublinear regret in the case of constrained MDPs, this is not something that we've rigorously derived, sorry. It's, however, it's been rigorously defined in a paper by Brendan and Tor in the special case of multi-arm bandits. So I would, if you're interested in how it's done in multi-arm bandits, I would recommend reading that. And the extension to an MDP should be quite straightforward, but we haven't rigorously defined it.
I see. If there is any other question from the audience, okay, Chava?
I always have another question. Yeah, this gamma star, since it's so central, I really want to get to the bottom of it. And I think that I do have a way of describing it such that I understand, like I want you to confirm that that understanding is correct. Okay, so let's say we are in this random MDPs. So there is this unknown hidden variable that identifies which MDP we are in. Call it age. With like that's a random variable. So it will have the prior distribution. Okay. Then we also are executing our policy, whatnot, like living happily, we collect data, we have a posterior distribution. And you're in an MDP at stage L, it's finite horizon MDP. And you look at the event that on the previous stages, the actions that were taken were optimal given the unknown hidden variable. Okay.
Yeah.
Like for each of the stages, you have these things. And then, okay, you arrived at this state. And so that's the event that you're talking about. This is gamma star. Okay. That was my question. Because it seemed to me that like what you wrote on the slides were not quite this, but you were very consistently explaining this. So I was like, okay, I need to understand this. I think that this clarifies it. Yeah. So the optimal, like whether an action is optimal or not, depends on this hidden variable, right?
Yes.
The latent variable. And that's the essential part. That's how you get the consistency and everything, like that you kept talking about. And I think that in your paper, in the appendix, you have a figure that kind of explains something about this. But yeah, like the slide with this gamma star definition, it doesn't seem right to me. I have to tell you that. Because if I look at just, like 2 stages, first stage, it's very clear. In the first stage, gamma star S is just like, oh, have I visited in the first stage S? That's the event. And gamma star SA is that like, okay, here there is already like this pi star S equals to A. That's a little bit confusing because pi star S depends on the hidden variables. That's not denoted here, but okay, you might say that, oh, pi star is actually random because it depends on this hidden variable because it depends on which MDP you are in. It's kind of like part of the notation, but like, I didn't understand that. But okay, now I understand. That's fine. But if we go to the next stage here, you have this big union over all of these other things. And that seems to me like, okay, so you're taking all possible states and actions. And okay, like that seems to me just giving the full space, right? Like, because you're listing all states, you're like given a state, you're listing all the actions. Did I take that action? If you list all the actions, yes, sure, like I took that action, like one of those was taken. So I don't think that this is the correct way of writing it, but like that's maybe just beyond the point. But we can take it offline as well. If
yeah, we could. If you have another way, I think like
I do. Like I can send a message and
yeah, sure. Happy
we can talk about it. Yeah.
Well, one thing to mention indeed is that since we're in the Bayesian RL setup, pi star is considered to be a random variable indeed. So I think maybe
that clarifies it.
That's the relationship to your comment about having these hidden variables. Because exactly. Indeed, in the Bayesian RL case, pi star is a random variable.
Right. Okay. Sounds good. It was just a clarification question. All right. And Brandon was asking, okay, but like that might be related to this. Yeah. Okay. We are already seeing this.
Yeah. I mean, Brandon and I spend a lot of time trying to like parse this object, and that's like the way we've tried to define it, which
is
a bit more rigorous. And I think the way this is formally defined is the right one, but happy to take it offline. I think another open question is whether our variational approximation is the canonical one to do RL as inference.
Yeah.
This is something we're not entirely sure of, in the sense that we cannot automatically get a policy gradient formulation, which should have been a nice feature to have. We need to kind of have in a few hacks at the end that I mentioned to get a scalable model-free version. And I think this is more on the side of the weakness of the way we do our variational approximation. And if we could find a tighter way at some point to do an upper bound, then hopefully we would be able, to exactly recover an approximation that can be used, that can be solved with policy gradient, like K-learning, for example, immediately. But that's more, a looseness of the analysis from a variational approximation. And we've spent quite a bit of time in trying to get this tighter, but haven't been able to so far. But if some people have some thoughts about how to do this, happy to chat about it offline.
Yeah. So 2 things, like back to whether this is the right definition. So if we take this union in the gamma star L plus 1 definition, let's say L is 1. So we take the union over all possible first fixed state and all possible actions. Go back to the left-hand side. You take the union over all possible actions. What do you see there? Like you get gamma star 1s only, because these intersections just go away because like you enumerated all possible actions. So you're not constraining the actions in any possible way. No, you're taking the union over all the states. Then you will not constrain the states in any ways. So it's like, I think that there is a way of writing this, but this is not the way. But It's just my.
Right, I see. Yeah, here. So here, the constraint on the state is, so maybe that's the way, like, you know, this notation which doesn't incorporate. I mean, this basically SL plus 1 is constrained by, of course, the transition dynamics, right? And so the constraint is implicitly here, which I agree, you know, isn't formally written in this event. So maybe there is a bit of a loose notation here, but there is definitely some constraint in, you know, what actually the next state SL plus 1.
I think you should just write like that gamma star A plus 1 S prime is the event where I1 star S is equal to A1, and A1 was the action that you took in the first stage. And then I2 star S was A2, where A2 was the action you took in the second stage, and so on and so forth, up to stage L. And then, in addition to that, SL plus 1 is equal to S prime, and that's exactly what you want to talk about here. These like formulas here, I don't think that they agree with this other formulation, but everything else that you were saying was consistent with this, so I think that like, everything is fine. It's just that like I got confused about this slide. Okay, so that was one thing. The other thing is that, you know, Miguel Lazar Gradila, he is in Kevin's group in GDM. They were also talking about this inferences planning and like do you see any relationship between the two works? Like what you were saying and they are saying is like, is it?
Yeah, we've been in touch with Miguel actually, where we had a meeting with him to try to discuss that. So they're mostly focusing on, you know, the planning side of it, and they're not at all looking into the RL problem. But I think it could be interesting to kind of combine the two works, but it's not something we've had the time to explore. But yeah, to the best of my knowledge, their group is only working on planning.
Yeah, if you don't have any uncertainty about the MDP, your method should be able to give you the optimal policy, right? Because otherwise you would have regret.
Yeah.
So you must be solving the planning problem at least.
Yes, exactly we are. And actually what's interesting is that basically if you look at algorithmically what the algorithm is doing compared to, you know, vanilla RL is just adding an exploration bonus, and it's adding entropy regularization, but that is weighted by something. And the key idea is there's no uncertainty, the exploration bonus goes away, but also the weight in front of the entropy regularization goes away. And that's why, you know, to the limit of infinite data and no uncertainty, we exactly recover the traditional RL formulation and not the entropy regularized, you know, maximum RL. And this is why we're saying we can get, you know, no regret.
Okay, can you go back to your algorithm slide so that we see this? Okay.
Yeah, here. So basically, the idea is once, if we have no uncertainty at all, then we're going to have sigma that's going to collapse. So basically, this optimistic reward that's going to collapse, and also the taus are going to tend to 0 to the, you know, limit of no uncertainty. And that's the very nice thing, is that basically the
why is tau tending to 0?
So basically, if like so.
When you're solving the min-max problem?
Yeah, exactly. When we're solving the min-max problem, we basically have actually.
Because if you have no sigma, then like the optimal choice is tau equals 0. Exactly. Tau is non-negative, right? Okay.
What's interesting is actually there's a closed form for tau.
You have the max min, right?
There's a closed form for tau, and we see that it basically directly scales.
So from their perspective, though, then this is kind of trivia because they wanted to use probabilistic reasoning as a way of solving difficult planning problems with large state spaces in MDPs, and your work is kind of not speaking to that, except that you could say that, well, okay, just throw in your neural networks, and like we have this neural network way of doing things, and like if that works out, then this is solving the planning problem because it's solving the harder learning problem.
Exactly. Okay. Yeah.
Okay.
But I think that's a key insight, and it's, you know, since we're talking about entropy regularization a lot here, the key difference is that with this, like, you know, weight the entropy regularization that decays to 0, then we are recovering the original RL problem, which is very different compared to works that study entropy regularization, but ultimately what they care about is this kind of different augmented RL problem, which is this maximum entropy RL, and it's a bit unclear why should we care about that transform problem and not the original one. Yeah. What this is saying is actually entropy regularization. It's an exploration scheme, but what we ultimately care about is the original problem where this tends to 0 with 0 uncertainty.
So when you go to deep RL, then you have some neural network representing both tau and what do you need, lambda?
Yes, exactly. Yeah, exactly. So the way we do it in deep RL for the approximation in the experiments, which was working quite well, is basically now we optimize over policies so that we can basically use policy gradient formulation. And since in the previous slide with the minimax game, actually tau has a closed form solution that depends on sigma. We basically we set tau, instead of learning tau as well, we basically set it as scaling as the
I see.
So that we basically have this. But like a tighter way would be to learn the taus as well, which is definitely possible. Yeah. It's just that basically setting taus.
This way, at least you're avoiding the min-max problem.
Exactly, we're avoiding the min-max.
It has the style. And then the novelty is that you are introducing this uncertainty weighting in the policy entropy regularization.
Exactly.
That's the whole thing. And so when estimating the uncertainty bonus, how do you do that?
So we use an ensemble of reward predictors. So this basically this is also parameterized by a neural net. And so we have 10 reward predictors. We take the standard deviation over that. So when I say reward, it's really they try to predict what's the local reward at each state action pair. This is parameterized by a neural net. We take 10 of them. We take the STD of that, and that gives us the uncertainty bonus. And so commonly in deep RL literature, they use it just as an uncertainty bonus here. So this optimistic actor critic. Here, what we advocate is also to make it as a weight for the policy entropy regularization. And what's really nice is, when the agent has learned and sigma hat tends to 0, then this regularization drops. This regularization drops.
Yeah. So what if I put you in an environment where you know exactly the reward function, so there is absolutely no reward uncertainty? You can try to pretend that there is reward uncertainty and piggyback on the top of that. Would you then just recommend doing that? So basically you would be adding noise to the reward just for the sake of keeping exploration alive.
Yeah. I think here, more on a practical level, there's a rich literature that studies different ways of having uncertainty bonus.
That seems to be necessary.
The one we're using indeed assumes that the reward are unknown, because otherwise it would trivially be 0. But then there are other ways of
so it seems that because of this objection, it is necessary for an algorithm that is guaranteed to work with this approach that's on the screen. That you add noise.
Exactly.
So that you make sure that so then we are in the realm of these randomized methods where you're adding noise to your data. That's interesting. Okay, very cool. All right. Thank you.
And in reading the paper, there was a question about this sigma. To me, when you prove the regret bound, then you have that the sigma is proportional to the inverse of the visit counts.
Yes, exactly.
Pair. And you say that this somehow comes from the assumption on the sub-Gaussianity of the reward, but can you just
So
explain a bit more why the sub-Gaussian parameter is upper bounded by the inverse of the visitation count?
Right. Okay. So here the assumptions that we have is basically this bounded mean reward and sub-Gaussian reward noise. These are, standard assumptions. The interesting thing is that these two assumptions necessarily imply that the mean reward under the posterior is going to be sub-Gaussian as well. And so here, the sigma squared is this sub-Gaussian parameter. And in this case, we basically have the standard property that it's going to tend to 0 as we collect more data at a rate of 1 over visitation count.
Okay.
And so this is why we can basically, then apply the pigeonhole principle and get a square root of t regret bound. So it relies on these like two standard assumptions here: bounded mean reward and sub-Gaussian reward noise.
Do you really need this Dirichlet prior over the transitions for the proof to go through?
So we don't need it at all for the known p case, of course. It's more for the
No, there are no p.
Yeah. And here, so we rely on it because to have this generic reduction, basically, you know, we're gonna we like the math behind it. It's on stochastic dominance arguments, right? So the expected value function under this is going to be upper bounded by this, and for this we need like a result that was proved by Ian and Ben on Dirichlet-Gaussian stochastic dominance, or second
Couldn't
order.
just that be a concentration argument or something? I mean, like, I would be very surprised if it was critically relying on this Dirichlet business.
So well, I mean,
go wrong.
It's an open question, but existing works also need basically this Dirichlet prior.
Sure.
Just to have this like second order stochastic dominance between like a Dirichlet and a Gaussian. But maybe there is a way to relax. That would be great, because I agree that it's quite a strong assumption.
I mean, like why? Like it doesn't seem like, intuitively speaking, like essential. It's like I can intuitively understand like every piece, and it doesn't seem to involve any Dirichlet priors. Okay.
Yeah, but this assumption is quite standard, like in the in the PSRL literature.
Yeah.
But I agree.
Let's not hide behind standard assumptions just because someone else did it. It's like we can be better.
I agree.
Right. Yeah. Okay. Very cool.